Okay, so the natural extension, of course, to finding stuff is to make a good recording of it. And like anything else, there are parts of our job that are pretty pedestrian, pretty easy, but where we earn our money is on the difficult stuff, the stuff we have to reach for. So it's really good to have all of your best stuff together for some of these very faint pieces of evidence, and an understanding of the process, both in terms of the light and the photography part, lets you do a couple of things. It lets you troubleshoot. So if something's not working the way you hoped it would or you feel it might, then it can help you make another decision, either a different filter or different goggles or different excitation. But also, increasingly, we get called on to explain ourselves more in court these days than I ever did in the first part of my career. It got to be, at least in my experience, and you can tell me your experiences, but when the defense found out there was fingerprint evidence, it was basically Monty Hall time. Let's make a deal in the hall. And with the exception of homicides, of course, but those days have changed. And when I started doing identification work, there were basically two techniques for finding fingerprints, one for porous, one for non-porous. Non-porous was powder, and porous, when I first came in, was silver nitrate, soon to be replaced by ninhydrin. Well, we now have literally dozens of techniques out there that we sort of have to stay on top of, at least know about if we haven't used them, because it's been my experience that nothing too much in terms of defense strategy has changed. They don't care if you did 11 out of 12 things, they're going to talk about the 12th thing. The emphasis is what was not done to kind of shed doubt on your credibility or the credibility of the process. And of course, if you'd done that 12th technique, you would have developed the fingerprint of the guy who really did this, not his client. So it's really important to know, I think, to be able to speak with a certain amount of authority on how these things work, and to be able to say, yes, that was an option, but we do this, and it's virtually the same chemistry, it's just a different approach, gives you about the same results, that kind of thing. So we have conventional photography versus luminescence photography, because I'm sure everybody in the room is conversant with conventional absorption and reflection photography. I mean, we've all done that throughout our careers. We may have optimizing the signal-to-noise ratio as simple as simply using a contrast filter. So if we are photographing an ninhydrin fingerprint on a document and there's green overprinting, we know that we can use a number 58 tricolor green filter, which will do two things. It'll drop out the green writing, and it'll also darken the ninhydrin. So that's one analog or optical example of optimizing signal-to-noise ratio. Well, we're going to be doing the same kind of thing in the luminescence thing, but there's a different approach. There's a different structure to luminescence photography. So if we take a look at the subject and we compare the conventional subject to the luminescent subject, when we photograph in the conventional sense, if I'm going to take a group photo, what I'm doing is recording the relative amounts of reflection and absorption from this group. So obviously there's lots of reflection from the light surfaces and not so much from the dark surfaces. And then of course, as I mentioned earlier this morning, the color rendition by selective absorption of that white light. So it's just the way we see the world. There's nothing really too different. But the important thing is we're photographing a percentage of reflected light. In the luminescent side of things, we want to see and photograph 0% reflection. If there's any reflection, we're doing something wrong, and we're not getting the best results. We need to have that barrier filter, the one we either wear on our eyes or the one we put on the lens of the camera, to block 100% of the reflected incident light. So that laser light, that poly light, once it causes that stuff to fluoresce, it's done its job, and it's a pain in the neck from that point on. So what we need to do is make sure our filters are specific and efficient enough to do that job. 100% emission, that's what we shoot for. Important safety tip, laser portraits are not terribly complimentary. This is actually a colleague of mine who was alive at the time this was taken. It was taken with science in mind. In ordinary white light, he has a full set of apparently natural teeth, but the one in the center is obviously a China clipper. Here we have very ordinary and normal looking young woman, happy to be here. This is in the absorption reflection mode. And here we have her laser portrait. So as I said, we live in a fluorescing world. This stuff is going on all the time. We just have to set up the situation where we can see that.
What's on her face?
I was careful not to ask. Without putting too fine a point on it, the list is open-ended.
It's Lewinsky.
No, it could well be the you pick up traces of, and we get back to the detection sensitivity of luminescence. My gosh, that could be some rhodomin she picked up somewhere, or some other fluorescing chemistry, and just, you know, we are always doing this kind of thing. And it reminds me of a situation when I was right back in the exciting time when we had our first laser, and the commissioner of the OPP had an open house for the press, and I was asked to stay after hours and show them the laser lab because, of course, we were the visual. Who wants to come in and look at filing cabinets and typewriters? That's pretty boring. But when they wanted something visual, something gripping, they always came to ident because what we do is so visual. So I had a group of people from the press, normal, well, as normal as the press ever looked. But anyway, about 12 people in the room, and the lights were on, and they looked every bit as normal as you guys do. When the lights went out and I started explaining about wavelengths and barriers and stuff, I noticed there was some giggling in the room, and they're all turning around and looking at this one woman who is outside of the area of the, she's just getting some of the scatter from the laser, and her lipstick is fluorescing like blazes. So it looks like a pair of disembodied lips talking in the dark. And she goes, "What?" Because they're all looking at her and giggling. So we had to get a mirror so she could actually see what was going on. But the offshoot of that was they started looking at each other with a more critical eye, and there was one guy who had a pair of very normal looking pants on, but with the lights out and the laser on, it looked like his pants were going through puberty. Hairy all over the place, and yellow stains on his pants. So, as I say, laser portraits are not terribly complimentary. They're great from a scientific perspective for reaching out and detecting stuff we would otherwise not get, but that's about the extent of it. And just to show I'm not being a sexist here, now for whatever reason, we don't have quite the same, he's got a great set of teeth, but we don't have the same kind of, shall we call it, arbitrary fluorescence from this individual. But the point of this is we live in a fluorescing world. It's going on all the time, and it's insidious. We can miss it if we're not careful. I heard some talk at lunchtime about it makes you wonder what we do miss, and I've wondered that for the last 30 years. Because a lot of the things that fluoresce inherently, as I said earlier. They don't scream at you. It's not like DFO or rhodamine 6G or indane-dione. They require a lot more careful look. An interesting thing we found, too, with luminescence, both detection and photography on metal, is this is as black as you're ever going to see anything. If you get a new coin and put it on the table and it isn't allowed to pick up reflected long wave light that will go through the goggles, it looks like a hole in the table. And that's a kind of an odd thing to be looking at it, so it looks a little abnormal. This actually came from a case I worked on, an extortion case, and a call was made from a phone booth. So we got the cash box from the phone booth, and it was my luck there was about $400 in quarters in there, rather than they just clean it out before this guy made his call. So every one of those coins was processed with cyanoacrylate and rhodamine 6G. So because metal has absolutely no fluorescent response, nothing, everything you see here is deposit on top of it. And there were actually, I think, 3 usable prints on the coins that came out of that box. You can have challenges in the conventional photography world that are solved quite nicely when you're talking about luminescence. This is not an eyeball. This is actually a brass door pull, and it's from the Ontario Police College, and it's one of the training items that they use. We put blood prints on it and then process them, or get the class to process them for enhancement and then photograph them. Well, the black pupil, as it were, you see here, is actually the reflection of the lens barrel, because it's highly reflective surface and it's a fairly tight curvature, so it poses a bit of a challenge, because after all we're dealing with selective reflection from different parts of the subject. However, fortunately, LCV, which is the developing chemistry in this case, fluoresces quite nicely, and when you take a photograph, you're not getting the reflection. All you're getting is the emission from that LCV, and you're challenged even to say that that is a curved surface. There's absolute, so that's one of the cases where it can. Perhaps we could just shut that light off for a moment again, please, if you don't mind. Anyway, beautiful print, photographed very nicely. Thanks. Every one of these surfaces is a curved surface, and you can't tell. So the problems that you run into with specular reflection from a curved, shiny surface, if you're photographing in the luminescent mode, they simply don't exist. I mentioned before that we've used in light source and laser photography and viewing, we've used unconventional filters, things that were never intended when they were first manufactured for the viewing and the photography of evidence. They were used for spectroscopic analysis. And we come now to talk about narrow bandpass filters, which are, again, an unconventional filter that was not previously used for photography. They were used to measure and limit the spectroscopic response of certain chemicals. So if we look at the typical situation, this represents the desirable fluorescence that we want. And this represents background fluorescence. And I'm sure everybody has seen situations where the background fluorescence is at a wavelength and or intensity even superior to that of the fingerprint. So in this particular case, your signal-to-noise ratio is not very advantageous. And this is one case where that barrier filter, which serves us so well most of the time, isn't cutting it anymore. It's not specific enough because it's like a door in the spectrum. Everything on that side is blocked very efficiently, and everything on this side is transmitted. So we get both the fingerprint and the background fluorescence coming through. And as I say, that doesn't always work. But what can work is if we have a very narrow band pass filter, which is far more specific. And these are not absorption filters the way you see with the goggles, where you look at them and they're just orange plastic or orange glass. These are called interference filters, and they work on a different principle. And because of that, they are a lot more efficient. That principle of interference allows them to work much more efficiently and with a steeper curve, a more selective curve than the absorption filters do typically. And if you want to see an interference filter, just look at the ones that are in your light sources. Those are interference filters. And typically you'll look at one and it will just look like a mirror, sort of a silvery surface on one side and usually a gold surface on the other side, and you don't know the true color of it until you actually look through it at a light. But what we would do here is find the normal emission peak, at the point at which our desired fluorescence is the strongest, and get a narrow bandpass filter that peaks very similar to that. And really what you'd like to do, ideally, is have that filter fit over your fingerprint output like a glove over a finger. And that way, instead of your signal-to-noise ratio being here to here, now it's here to here. So you can make a significant gain in the intensity of your fingerprint versus your background. You don't need this all the time, but there are occasions where it has made a huge difference. If you have sharp eyes, you may be able to see a little bit of ridge detail in the center here. This is a Canadian $10 bill, or $9.40 down here. And you can see a number of things are happening here. You can see that, first of all, the paper itself has a dull orange fluorescence. And you may just be able to see the orange fluorescence of the exhibit marking here. Then you have like a lemon yellow ridge detail area, and then some kind of spot fluorescence there about the same color. Now, if we are to, this is with the bandpass filter, the very non-discriminating typical orange filter that's in our goggles. Now, if we are to use a bandpass filter, we can see a number of things have happened. First of all, our signal-to-noise ratio is much better on the ridge detail than it was previously, and the bright orange marking before now looks black. Its fluorescent response is just totally knocked right out. And this is typical of these filters. They are so specific. They are what I would call surgical. So you can actually optimize desirable fluorescence when it's being interfered with in that way.
Brian?
Yeah.
How specific are they? How many, like?
10 nanometer bandwidth.
Okay.
But you can get them in 40 nanometer too. I like the 10 nanometer one. It really makes a huge difference. Now they're expensive. They're like $300 a piece, but I still have the one I bought in 1979. So amortized over 35 years, that's not.
Don't you find that after a while, what you get is you get the creeping in of that fog from the edge of the glass? Because I've got some that are close to 15 years old, and it's really starting to creep in. You get a fog, so essentially I'm only looking through the center part of the lens. Have you ever had that?
No, I don't know who manufactured them, but My,
Who had good glass for a while there too was the old Polylite filters, you know, the narrow band.
oh, they're
pass.
great filters.
Yeah,
They're great
yeah,
filters.
Like I say, I'm the old
Yours are
Polylite.
starting to go, are they?
Yeah, yeah.
Filter fatigue, that's a new one on me.
Well, okay.
You just can't get good help
No,
anymore.
you can't.
Well, it may be time to replace, but I'll show you the one I have that was bought in 1978 or 79. I forget the exact time, thanks. And there is no deterioration, but I have seen the kind of deterioration, the edge deterioration you're talking. You get like a vignetting.
Yeah, you get a
effect.
fog. You really
Yeah.
can't see through it. You can see through the center, but the edges are starting, you're losing it. That vignetting around the edge.
I'm wondering if that isn't a sign of cheap filters. Because
Yeah.
the one I got is still as good as it ever was.
Damn Polylite.
There's nothing cheap about polylights.
Well, I have, there's a company called Mel's Griot, and I like their fillers a lot. I bought quite a number of them over the years, and they have worked very well. An interesting thing, though, they do not work all by themselves. You'd look at this and you'd say, well, if it's that selective, then it's even more selective than the typical cutoff filter, the high-pass filter. So there'd be no chance that it's going to allow passage of any of my exciting wavelengths, but you'd be wrong. And what I found is and I still don't understand the physics of this completely, what I know now is that until they come up with a better filter, I have to sandwich the two together. Yep.
Stack them.
Yep. Now that's a big filter factor, but it can make a huge difference in your results. So we'll just show you that. Like that one's a result of stacking. A couple more examples of what kind of difference this can make. I should mention too that Polylite, Rofen, have a narrow bandpass filter that they made available to me, and it is a 40 nanometer bandwidth. It's not as specific or as tight as the one I got from Mel's Griot, but it did help in some situations quite nicely. But anyway, we have some comparisons here, and before I go further, it's going to look initially like I'm pushing the laser and knocking the Polylite or knocking the forensic light source, and that's not it at all. This is one of the cases, this question of untreated fingerprints, where I have found the laser to be superior in most cases. But I come back to what I said earlier, this inconvenient truth that these two things are complementary and they are capable of, on any day, any exhibit, outperforming the other one. And again, as I said before, this fluorescence doesn't scream. Can you see anything at all there? There's just a vestige of ridge detail. Now that's the bandpass filter with the Polylite. Now you should start to see, can you see some ridge detail here now? You think this is quiet. It was a lot quieter with the regular filter. So I'll show you some examples of the difference. So this again is the same surface, one with the Polylite and one with the laser. And what I believe to be the case is the two light sources are kind of like comparing a rifle and a shotgun. One does not do everything the other one does. You use them for different purposes. And the rifle, what I would call the rifle, is the monochromatic single line laser, and the shotgun, hence the shotgun approach, is a whole bunch of wavelengths there, and it's great in terms of crime scene CS examination for hairs, fibers, and anything, because you can, it's going to cause a whole lot of things to fluoresce because there's a third of the visible spectrum, very bright, that's out there exciting whatever is to be had. When you find some kind of a disruption, some kind of a disturbance that may be something important, then you can go to a more specific wavelength of light if you have the light source, or if you have the laser, you're probably going to be doing that anyway. So what happens here is we don't have a whole lot of difference in the overall brightness. It's just the signal to noise ratio is better here. Now when we go to the next step, which is the narrow bandpass filter. If anything, it made things worse with the polylight, but it really improves the detail on the laser side of things.
These are all test prints, like you know,
Yeah.
greased them up. They're not.
Not greased them up, but they're not case prints.
Right,
They're-
okay.
And they're not meant to say that the laser is going to do this all the time, but it's to get
It's all controlled, right?
yeah. And what it's meant to show is how the filtered bands of light are not as sensitive to some of these as the laser can be. And it reflects what my case experience was for the last 30 years. Again, polylight and laser, and this is a good representation of what you see. It's very, very quiet. And then again with the narrow bandpass filter. So, if we look at the light sources, conventional versus luminescent, conventional light we could use available light, that we can use flash, we can use fluorescent lights, we can use tungsten light. But the one thing they all have in common is that they're all a full visible spectrum. So all the representative parts of white light are present. All of the wavelengths from 400 to 700 nanometers. On the luminescent side, when we have a light source, we can use lasers. We can use forensic light sources. We can use UV. But they are either monochromatic or they are a filtered source with part of the visible spectrum or part of the UV spectrum. So there's a difference in the subject, as I showed you, and there's a difference in the light sources that we use. Now, when we talk about light sources in conventional photography, things that are important are the angle of light. And I'm sure everybody, either in training or in reality, has had occasion to look at a tile floor with oblique light. And Bill Bodziak's got a great illustration in his book of just that, where he's got a room lights on shot showing absolutely nothing on the floor, and then without changing anything else, the room lights are off, and he's got an oblique light just touching the surface, and there's a pretty nice footwear impression on the floor. So angle of light is very important. We have direct light, we have diffuse light. Sometimes diffusers, particularly with regard to use of coaxial light. So the character of the light, aside from the wavelength, is quite important, and this can have a huge impact on the clarity of your subject. Luminescence, on the other hand, the angle of light changes the intensity, so you're not gaining anything by dropping down and scattering, you're just reducing the amount of fluorescence, because it's not registering that differential in reflection. All it's registering through your filter is whatever fluorescence you've caused with it. And so it's not helpful or productive to drop your angle of light when you're using luminescence as a detection source. So really what you want is probably as close to coaxial as you can get to maximize the power you're getting from your machine.
Brian, didn't you have one example of using oblique laser light with that shoe print earlier on?
Yeah, but there's no filter.
Oh, okay.
Yeah, thanks for reminding me. That one was just straight laser light recorded through the camera with no filter. And yeah, thanks for reminding me of that, because I think, again, the fluorescent, or pardon me, the reflective properties of one wavelength of light are different from the whole group of them in unison. Mm. They have to be, because they do different things by virtue of their different wavelengths. It's kind of like you hear a beautiful soprano voice, and then you hear that same voice as part of the Mormon Tabernacle Choir. That voice is still there, but it's performing in concert with a whole bunch of others. And that may be nice, but it's not the best occasion to hear what that one voice does, if I can use that metaphor. So I think that is why the identification officer, when he saw that print, he used his flashlight and he could just barely see a disturbance there. And he was with me when we examined the door with the laser light at a very low angle, and it just blew him away when he saw the print come up. And that's not something I have followed up on. That's the only example I have of that, of use without any kind of barrier filter. So once again, all of the qualities, all of the different characteristics of your incident light that are important in the reflected mode don't matter a hoot in the fluorescent mode because they don't get that far. None of that reflection makes it through your barrier filter. So direct or diffuse, the only thing that's important about a diffuser in some cases is that you have uniformity of light and you don't have a interference pattern if you get your LED source too close and you get the pattern of the LEDs, or LEDs rather. So you have to back it off enough that your lighting is uniform. That much is still true. But as far as the actual character of the light in terms of being direct, diffuse, or angled, makes no difference. So you want to shoot for uniformity across the area of interest, which is true of any photograph we would take. And the bottom line is, if you see reflection through the goggles, i.e. if you see blue or green light hitting your eye, something's wrong, or in the image area of your camera. So in terms of troubleshooting, we have some choices. We can change the excitation, that is the primary filter. We can change the barrier filter. We can consider a narrowband filter. Before we go to the questions, you can look at how many people here have a polylight? Okay. Now you know that you can use the 505 and wear your orange goggles and it works just fine. But if you go to 530, those orange goggles don't work anymore because you're getting green through. So you need to switch to red goggles if you're going to use a 530 or a 555. But on the other hand, hold on here, 505 works fine, 530 doesn't, but we can use a 532 on the laser and those orange goggles still work just fine. And the reason is the filter doesn't have to work nearly as hard to block that one wavelength of light as it has to block the whole band that's being transmitted. So you've got about a, I wouldn't want to be held to this, but with the 505, you've got something like a 30 to 40 nanometer bandwidth. And that's a lot of wavelengths of light for that filter to block. But it still does it because it's far enough down, it's short enough in wavelength that it's going to block it. But when you get up to 530, your emission width is again 20 or 30.
On either side. It's 20 on either side, so it's actually up all the way to 550 on that side.
There you go. So you're probably 510 to 550, something in that neighborhood. And it's simply too much for that orange filter to block, and you get that green coming through, and it's image destroying. But on the other hand, I like to think of the laser as surgical because it's one wavelength of light only, and if you've got the right filter, it's no contest. It's not getting through, so your results can be very clean. And that's really, really important when you don't start off with a huge signal-to-noise ratio. Okay, anybody have any questions? Anything I didn't cover, or experiences, problems in photography?
You asked me to remind you about the one case that where you did inherent fluorescence at the scene and then other processes afterwards. You wanted me to
Yes, thank you, Leslie. Yeah, Leslie asked a great question at lunch about the getting back to the serial killer I talked about. And so we had the home for as long as we wanted it. You don't always get that luxury in a homicide. But first of all, it was examined by forensic light source, the Lumilight. And nothing but a few fragments, nothing worth photographing, was found. And then my staff member went in with the laser and found and photographed 40 untreated impressions on the walls, cabinets, door jambs, and so on. What I didn't say this morning, and what Leslie asked me about at lunchtime, was that after that, he then sealed the entire house. He went around with tape, sealed all the windows and doors, and he filled the house with iodine fumes. And it was a pretty heavy-duty environment in there. Even 2 days of airing out, he still had to wear a Scott air pack to go in and look. But the result of that was he got 4 fingerprints that did not show up by laser. And none of the laser ones, there was no crossover, is what I'm saying. So after that, he then got a roller, a paint roller, and he painted the walls with ninhydrin and got 16 more impressions. So the bottom line on all of this is that not one fingerprint was developed by more than one technique. But we shouldn't be all that surprised at that. When you think of the possible ingredients of any fingerprint, organic salts, inorganic salts, lipids, uric acid, urea, sebaceous oil, the list, amino acids, 21 amino acids. So that's greater number of permutations than the state lottery. And it can change day to day depending on the person's, if they're into that sympathetic nervous system, you get an adrenaline jolt, maybe you're putting out a lot more than yesterday when you were in a state of rest. And we know that the iodine depends on the presence of sebaceous oil or sticky, some sort of sticky oil. We know that there are other things that fluoresce intrinsically. We know that B-complex vitamins like riboflavin and pyridoxine fluoresce, but we also know that contaminants, many contaminants will fluoresce. And then lastly, we have an amino acid process, ninhydrin, which develops a whole bunch more prints. So it shouldn't surprise us that if we have a fingerprint that's got A and B in it, and our reagent targets C, we're going to miss that print. It's one more reason why, when we can, on the cases we can, sequential processing is a great idea, because you take advantage of different properties of the print and more chance of getting what's there. So thanks for reminding me.